All right, let's dive in. Today, we're taking a tour of our planet's most inhospitable corners. I'm talking about places that push the absolute limits of temperature, pressure, and chemistry. Environments that honestly seem more alien than earthly. So let's get ready for a journey to the very edge of what's possible.
And that's really the key right there. You see, these aren't just geographical oddities or fun facts. They are, for all intents and purposes, living laboratories. When we study them, we're not just learning about some weird spots on a map. We're fundamentally redefining our entire understanding of what it means for a place to be habitable. We're redrawing the very boundaries of life itself.
So our journey to the edge is starting right now. We're going to explore the incredible ways life finds a way, even when it seems impossible. First up, we're tackling the most fundamental challenge you can think of: temperature. We're going from the coldest cold ever recorded on this planet to the most blistering, scorching heat its surface can possibly generate. Okay, let's start with the cold. This is the East Antarctic Plateau, and it is, officially, the coldest place on Earth. Now, how does it get this cold? Well, it's a perfect storm of factors. It's incredibly high up, over 3,000 meters. The air is bone dry, and during the long polar nights, any and all warmth just radiates straight back out into space. At these temperatures, steel can literally shatter like glass. It is just unimaginably frigid. And now, let's do a complete 180. From the ultimate cold, we pivot to blistering heat. The Lut Desert in Iran holds the record for the highest land surface temperature. And that's an important distinction. This isn't the air temperature you'd see on the news. This is the ground itself. The dark volcanic rock just soaks up so much solar radiation that it gets hotter than the inside of an oven. So how on earth does life cope with this stuff? Well, in Antarctica, tiny microorganisms survive in lakes underneath the ice, with metabolic rates so incredibly slow that their life cycles are stretched out over thousands of years. Then in the Lut Desert, you've got what we call extremophiles, microbes that actually thrive in these extreme conditions. They have these specialized proteins that stop them from basically being cooked from the inside out. It's just a brilliant illustration that even in places that look completely barren, life is there, hiding just beneath the surface, perfectly adapted. All right, next up, we're shifting gears. We're moving from the horizontal axis of hot and cold to the vertical one, from the deepest, darkest trenches to the highest, thinnest peaks, where the real challenge is all about pressure. To even begin to wrap your head around the force in the Challenger Deep, which is nearly 11,000 meters down, just look at this. The pressure down there is the same as stacking 50 jumbo jets on top of you. It's a world of absolute, total darkness and just a crushing, relentless force. And here's where it gets so fascinating when you compare the two. You can see it in this table. At more than 10,000 meters below sea level, you've got snailfish that have evolved to handle over 1,100 times our normal atmospheric pressure. But then you go 8,000 meters above sea level to the death zone on Everest, and the challenge is the complete opposite. There's not enough pressure. There's only a third of the oxygen available, so life is pretty much reduced to microscopic organisms just riding the wind. Two opposite extremes, two completely incredible sets of adaptations. Okay, our final gauntlet. This one isn't about hot, cold, high or low. This is about places where the very chemistry of the environment is toxic, where it's more like industrial chemicals than any natural habitat you can imagine. Just take a look at this pH scale. Right there in the middle, you've got neutral water, nice and simple. But we are going to the absolute fringes. On one end, the Danakil Depression, with a pH near 0. That's literally the same as battery acid. And on the other end, Lake Natron, a caustic alkaline bath with a pH over 10.5, kind of like an industrial cleaner. So, in Ethiopia's Danakil Depression, you've got these bubbling acidic pools, intense heat, toxic gases, and yet microbes are thriving in this super concentrated brine. Meanwhile, over in Tanzania, the water in Lake Natron is so alkaline and so salty that it can calcify animals that die in it, basically turning them to stone. But get this, it's also a vital breeding ground for flamingos that feast on the salt-loving microorganisms that give the lake its crazy red color. So, we've seen fire, ice, crushing pressure, and bizarre chemical baths. But what's the big takeaway here? Why is it so incredibly important for science to study these hostile, out-of-the-way places?
Well, the Atacama Desert in Chile gives us the perfect answer. This place is the driest non-polar desert in the world. It's so barren, so alien-looking, that NASA actually uses it as a stand-in for Mars. They test their rovers there. Why? Because the microbes that manage to survive the extreme dryness and intense UV radiation are our best guess for what life might look like clinging to existence in the harsh Martian soil.
And really, that's the thread that ties all of these incredible locations together. They completely redefine what a habitable environment can be. They serve as these crucial models for what conditions might be like on other planets. But I think, most of all, they reveal something fundamental about life itself. It's not fragile. It is tenacious, it's adaptable, and it is absolutely astonishingly resilient.
Which of course leaves us with one final massive question to think about. If life can carve out an existence in battery acid, under the weight of 50 jumbo jets, and in the coldest voids on our own planet, then where else, out there in the cosmos, might it be doing the exact same thing?